Yeah. The next question that gets asked in the context of screening is, can there be tolerance to how frequently you get access to the data and how much you keep the state maintained or updated or refreshed, right, in terms of newer data that comes in, how accurate we want to maintain the state. So that's a very critical question that dictates basically the performance of your streaming application, how much time you take to actually process a new batch of data, new incoming data set. So here, state maintenance refers to the fact that there is state that's necessary for the application to do its job. We spoke about some examples of state, right? Like in the context of IRCTC. Then, if you don't have access to the accurate state, can the application still go about doing its business? In certain cases, absolutely not. Right? In certain cases, like for instance, the same IRCTC ticket booking example, if you don't have accurate inventory, meaning the latest set of accurate seats which are available for you to book, you could end up potentially having double booking. And that's disastrous, right? Because you don't want people to think that they have seats available only to come to the station on the day and figure out that, yeah, somebody else is actually occupying it genuinely, and they also have a paid ticket for it. So, in certain cases like that, the state refresh has to be accurate, has to be always up to the latest payments that have been successfully made and the latest tickets that have been booked. In some other cases, it's okay that the state is not maintained up to the latest levels. You can tolerate a certain level of delays or certain level of missed state updates. So the example here is, let's say you're talking about the customer interaction, right? The e-commerce setting, you're buying a shoe and you want to have personalized interaction because the customer is just not able to make up his mind to close the transaction. In that setup, it's all right if you don't have access to all of the customer's past history, right? So the state associated with that particular transaction, that he's had a shoe in the shopping cart, the shoe is like of type Nike and it's got a certain value, etc. That is important because that's what allows you to intervene and say, you need help and I can help you fit your shoe size. But the fact that he's a loyal customer, the fact that he's already spent 10,000 rupees over the last 6 months, it's good to have because it helps you improve your personalization, it helps you improve your conversations, but it's not a must. So you can tolerate that data not being available or that data not being refreshed up to the last minute. So that's a question that you need to ask. Now, the state also has an implication to how much time an application takes in processing data. So, if you need always up-to-date state to be maintained, you're going to have to spend resources for that, as opposed to being able to tolerate every now and then some state not being updated. So that has an impact on whether you're able to process data fast, and that in turn has an impact on whether you're able to always be up to date with all the data all the time, or you're not able to catch up to some of the data sets some of the time, etc. So the third issue, the third consideration that we'll have to pay attention to is the fact that performance issues almost always manifest as resilience problems. So we didn't actually define resilience at all, sorry, so I think we should do that first. Application semantics that we're speaking about here, all of these play a role only in terms of determining the resilience of the application. Now, why resilience? Why not something else? Why not, some other way of characterizing the application? So remember that the use case requires you to almost always respond in real time. And if you don't do that, right? If you don't actually respond in real time, the first instinct that you have as a business owner or as a developer is whether the application failed. Now, the application could still be very much running, right? Could be that it's slow, it's caught up with something, it's become very gated or bottlenecked on some other resource, or it's waiting for an API call from your machine learning model to succeed, and that's not happened successfully yet, etc. Could be a variety of reasons, but the moment the real-time guarantee of the response is broken, right, the first instinct that developers or business owners start to have is whether the application is running or not, or whether it's failed. That's why the inability to respond in real time is looked at as a resilience problem, because it feels as though the application is not running, it's failed and it's thrown an exception or whatever. But in reality, it could be running slow, it could be taking its own sweet time, like I said. So performance issues for streaming applications invariably manifest as resilience problems. And the moment it manifests as a resilience problem, then confidence is shaken, right? So that the business stops trusting that the software can be trusted to be always on. And that becomes a far more dangerous situation to be in. Now, this doesn't affect batch processing systems as much. Like, for instance, if you take an ETL, and that ETL takes 3 hours to run. If it takes suddenly 3.5 hours, that's okay. Like, nobody's actually going to sweat much. Because any which way, there isn't the expectation that you're going to get an answer instantaneously. You're going to get the output of that data processing once in 3 hours. And if it's not going to happen in once in 3 hours, if it happens in once in 3.5, then the extra half an hour of waiting that happens is not significant. So therefore, most users of that output, most consumers of that output will not even notice. Now, of course, if that 3 hours becomes 3 days, then obviously it's noticeable, and then people think that, okay, maybe the batch processing application is not working. Whereas behind the scenes it can be a performance problem. But that kind of a scenario is far more frequently occurring for real-time streaming problems. So performance issues have to be fixed, have to be taken very, very seriously. And because this is your stack, this entire thing is your stack, starting from hardware, through the persistent store software like message buses and so on, stream processing software, the data that goes through in terms of velocity, from the source all the way to the state application, etc. The performance could be a problem at any point, right? Because streaming is an end-to-end application, streaming is an end-to-end consideration. If performance affects anywhere in the stack, it's actually going to affect as a resilience problem for the application itself. So that's why the streaming context is a challenging context compared to the batch processing one. So what are the best practices? So we spoke about the stack in the previous slide. Here's a specific way in which to organize the stack. And this way to organize the stack comes from years of having done streaming code, right, in many different setups. Not just me, but also multiple different practitioners of streaming engineering. So let's take a look at the best practices one by one. First and foremost, let's take a look at the organization itself. So we spoke about how the application has state attached to it, and those two go hand in hand. But in reality, you see that the state is actually more intrinsically tied to the data. It's less about the application. Obviously, the state is storing information which is in the context of that application, in the context of the business process that the application codes up. But the state is more closely associated with the data. Meaning, as newer and newer data comes in, as those data sets get processed by the stream processing software, it gets updated in the state, and vice versa. Which means the state at a particular point in time dictates the stream processing that happens on a particular piece of data at a particular point in time. So these three things go very closely, they're almost tightly coupled compared to the state of the application. So in that kind of a setup, it makes sense to actually think about these three things operating in a way which has very little latency. Right? So the best practice here is to think about the persistent store software, like a message bus as an example, to also be responsible for not just the data but also the state. In which case, the ability for the stream processing software to operate on both these sets of information, the data and the state at any point in time, is much simpler to reason about. Because then you're only dealing with how does the stream processing software interact with the persistent store software, and therefore can I optimize those interactions? Can I make it much faster? Can I make it much less contingent on some other data processing happening at the same point in time? So make it as seamless as possible. So there is a case to be made for tightly coupling these different systems together, but still have some amount of loose coupling so that each of them can independently scale. So that's why the stream processing software is called out separately, but it reads data from the persistent software and then maintains the state that's necessary for the application within the persistent source software. The second reason why this kind of an organization makes sense is, as newer data set comes in, you might have newer processing that needs to happen, in which case you want to keep going through these loops and loops of data processing as fast as possible. You don't want to keep waiting for the first loop to finish and then trigger the second loop. Now, certain kinds of logic might not allow you to do that. Like for instance, if you're computing running balance, right? Like for instance, the payment processing for IRCTC, the successful processing of a ticket should lock up an inventory, right? Should basically say those seats are no longer available. Now, if a particular ticket processing is happening and you've got a time window of, let's say, 5 minutes to make the payment, at that particular point in time, you don't want some other parallel processing of a parallel reservation to eat up that particular inventory, eat up the same seats that you've taken up. Obviously, that's not a good thing to do. But if there's a parallel ask for a different inventory, meaning there is another person who's looking to book a ticket in a completely different plane, with different seats, then there is no reason why you can't process that at the same time, right? You can run both of these in parallel, and you can get more throughput from your system, get lesser latency for each of those different processes to run, so that the customer feels that it's got a good customer service. So that's possible only if you think about these as running independently, operating on its own sliver of data, partition of data, updating the portion of the state that it's supposed to be, reading and updating. So, therefore, each of these become one unit of work. This iteration of data stream processing state becomes one unit of work, and it operates at a very, very small granularity of individual data messages, individual state updates. So that's your level of granularity, not files, not 1 hour of data, etc. If you operate at that level, then you can operate multiple such parallel jobs for each individual data updates, so that you can actually have much better throughput. The state, which is maintaining the state associated with the application, like for instance the number of tickets that are available, the payments that are pending for a particular user, etc. That state is then becomes the gate that allows you to say to parallel processing of ticket bookings, do not book the same seats, right? Because the seats would be stored in the state, and the state will allow you to say, look, there's already somebody else who's actually blocked these tickets or blocked these seats, so don't. The other person who's actually trying to do that, he will have to wait until this particular payment happens or the time it happens. So the state actually allows you to control for shared accesses to the same piece of information or the same piece of data. Alright, so that's in terms of organization. Let's take a look at specific best practices. First and foremost, notice that in this kind of a system, anything can fail. Right? That's always been the mantra of a big data systems, right? Because these are built on commodity hardware, so anything can fail in terms of network and memory and so on. So if something fails, can I reason about what is the current progress that's been made by the stream processing? Is it already gone through data as of last minute or last second, last 5 minutes, last 10 minutes? What is the guarantee? That guarantee is an important feature of streaming applications, because if you don't have a guarantee, then you can never reason about, do I start the streaming application all the way from 30 minutes ago, in which case I reprocess all those tickets as an example, right? Resulting in duplicate payments potentially. Or do I start only from today, or rather the latest second, but lose out in the last 5 minutes that was supposed to happen, in which case that's also bad customer experience. So to deal with this kind of a scenario, you do what's called as checkpointing. Checkpointing allows you to record a piece of output of a particular output of processing and say that, look, I'm done with this. So please record this in persistent store and allow me to make progress. Then, after the checkpoint is done, if there is a failure, then the streaming processing application can go back and look at the checkpoints, all the set of checkpoints that have happened until the point in time. Look at the most recent checkpoint and say, look, okay, I'm done as of 5 seconds ago. Then we start the data processing again from 5 seconds ago. Right? So the checkpoint allows you to reason about what's the piece of data that you've actually successfully processed. Now, that's how you deal with resilience issues. You can actually make more informed guarantees that you're not losing data, you're not losing potential information. Obviously, the act of checkpointing is going to slow you down because it makes you force data to be read and written to disk. Right? Usually, a checkpoint is written to a persistent store like a disk, in which case the act of writing will block the rest of the application from running typically, or even if it runs concurrently, it still is like a non-zero load on the system. So checkpoint less slow performance a bit, but it's an extremely useful feature that's available. The second thing is second best practice is something what I call as hot potato principle. So imagine as though I've got multiple things to do. So again, ISATC, I need to book, I need to process the payment, I need to block the tickets even before I process the payment, the seats I mean. Once the payment is processed, I need to go register the fact that the seat blocking needs to be made permanent so that the seats are getting assigned. And then I need to go give an acknowledgement to the customer saying, look, the payment is processed, here's your seat. And then tell the customer, look, wait for a minute before you get the formal invoice. And then I need to coordinate with the invoicing system to generate the invoice and send it out, etc. So multiple things. All those things are sequentially laid out in some shape or form based on successful operation, successful processing of the previous step. So that kind of a setup, right? What you want to do is not do all of that work in one go, right? So imagine if you were the designer for the software which did all of this. One way to design the software is to say from start to finish, it's just one file of code. And that file of code does everything, right? Starting from ticket blocking all the way through to invoice generation that I talked about. So if that's happening in one piece of software, then for every new event that comes in the streaming fashion, the event start would be somebody saying, look, I want tickets for this specific sector. So from that point on, it's the same piece of software, the same code, which runs in one continuous flow, right? And that continuous flow needs to do like 5 different things, right? Interacting with many different systems. And by the time that's done, it's only going to be potentially about a minute, maybe even more, or maybe like 2 minutes because the user takes some time to do the payments, etc. So for 2 minutes, you've got one piece of software running on all of these different, sequentially data processing outputs. And in that time, nothing else can run, right? In that time, if let's say the user takes additional 30 seconds to pay, the software the piece of the software that's running for that particular piece of data, it's still on. It's still occupying compute cycles, waiting for the user to make the payment. While that's happening, the data is still fresh in its state. It's not able to checkpoint yet because it's not finished this entire loop. So that kind of a setup is something where to fail, you have to start all over again. The better way to design this is to think about doing the least amount of work that's necessary and passing it on to the next piece of software. So these 5 things that I talked about, break it down into 5 different pieces of software that needs to run, each running on its own version of the data, right? Each running on its own input, each producing its own output, which is necessary as input for the next piece of software. But the moment it produces an output, it's done, right? So that piece of software, that step can move on to the next data. Like for instance, I need to block tickets or the seats, right, in the inventory management system, so that somebody else doesn't come and pay for it. So if that's the first step, then the software that takes the input here is a request for ticket blocking, and acts on recording and blocking the seats in the inventory management system, needs to be only focused on that. And the moment it's done, the moment it blocks, it writes its output to a state. It writes its output to the persistent store saying, look, I'm done, checkpoint me, and I can move on to the next ticket blocking, right, the next request. Meanwhile, the next step that needs to run, which is basically the payment processing, can listen can notice for the act of the previous step writing that the tickets are blocked or the seats are blocked successfully. The moment the seats are blocked successfully, this payment processing step gets triggered and it picks it up. Right? It picks up this piece of information, then acts on top of it. Right? And then it does its thing, and once the payment is processed successfully or failed, it writes its output back. And then the next step picks it up, and then the next step picks it up, etc. Right? So this kind of a way of organizing things is basically this part around, read the data, write the state, read the data, write the state. Each step is its own loop, right? That's basically what's called as the hot potato principle, meaning it's after you're given a hot piece of potato or a hot piece of coal, right? You don't want to keep holding it until all of your different activities are done. Instead, you want to do the minimum piece of activity that you're responsible for and hand it off to the next person. Like if you've seen how, for instance, at a construction site where the bricks which are meant for the construction are laid out, right, as a big series of, as a stack of bricks, right. So when the bricks get unloaded from the truck, which is bringing it from, let's say, from a far off location, it's not one person who climbs up the truck, takes the brick, climbs down, comes and stacks it, goes back, etc. Right? It's a very, very wasteful way of doing things, and it takes enormous amount of time. And secondly, it introduces a lot of load, a lot of overheads on that one individual, resulting in that person likely to fail, right? Because he might get overworked, etc. Instead, what you see happening is there's one person sitting on top of the truck who throws the brick. There's a person who's responsible only for receiving the brick. Then he or she hands it off to the person who stacks the brick. So 3 people, each doing something very specific. And at any point in time, if somebody is slow, then everybody else becomes slow. Like for instance, the person who's throwing the brick from the truck, if he slows up for some reason, right, if he decides to take a nap, then the other two are not doing any work at all. Likewise, the person throwing the brick, if he has to wait because the person who's handing it to the person who's stacking, the in-between person is not ready to receive because he's had an emergency, he has to go to the toilet or whatever, right? Or he just has to sit down and drink some tea. Then again, the rest of the pipeline stops. So, whereas in the hot potato principle, the moment you receive the brick, you just pass it on. Do your work, pass it on. You're done. So that's what the hot potato principle for data streaming means. Notice that this consideration does not apply to batch processing. In batch processing, you could do like 3-4 things together in one code, and probably that's better because for readability purposes, you know exactly what's happening. And there is still merit in decoupling, obviously, because you can scale things independently, but you're not going to be worried about taking the least amount of work and spinning up different processes for that. Because in batch processing, you might have more efficiencies by clubbing together a bunch of related pieces of code together. Alright, the next thing here is about source playback. So before we understand about source playback, let's talk about these two semantics here, axes points and exactly points. So when you deal with data in a streaming fashion, oftentimes you have to think about, am I giving the guarantee that I'm processing the data successfully? And if I'm giving the guarantee, am I processing all the data exactly once? Or am I processing some of this data multiple times? Why would this consideration come into play? It comes because all of the issues related to streaming manifests as a resilience issue. Meaning, it's also the software stopped working if it didn't respond in real time. If it did not do its job in the stated within the stated time, right? So if that happened, if it manifests as a resilience issue, the common question to ask is, do I stop the application? And in which case, if I start it again, where does it start from? Right? You could say that if I've checkpointed myself, I'll start from where I checkpointed last. But even though I checkpointed last, let's say 5 seconds ago, in the intervening time period, in the last 5 seconds, before my performance went down and it manifests as a resilience issue and I have to start again, right? In this 5 seconds, did I process the data successfully? Or did I process the data but not write the output? Or did I not even process the data? Did I not even get started with reading the data? I don't know any of that. I don't know the answer to that. And if I don't know the answer to that, if I just blindly start again from 5 seconds ago, I could actually have processed the data once already. But because I started again, I could process the same 5 seconds of data again. In which case, I will not be able to give a guarantee that I've processed the data exactly once. I might have actually ended up processing duplicate data multiple times. That might or might not play a role, or might or might not be important for your application. For certain things like payments, it's very important. For certain things like, reaching out to the customer and saying, look, I think your shopping can handle. It's not that important. It's okay if you ask twice. Right? So the source application, rather the real-time application, has a very big impact on what guarantees you have. But the guarantees are also determined by two very, very important factors here. The first is what's called as the playback at the source, and the second is how persistent a store is the persistent store. Right? Is it actually able to checkpoint for long periods of time? Can I get that access? Can I get the latest checkpoint? Can I get the latest state that's maintained in interactive latencies? I don't have to wait for a couple of minutes or etc. So that's all part of the persistent store guarantee. But let's take a look at the source playback, which is a new term that we've seen for the first time. So the playback refers to whether the source can give you the same data again if you ask for it. So the analogy here is as though you have a piece of tape, right, which is playing back an audio. So you want to go back and listen to the same audio, let's say the song. So you rewind the tape and you play it back again. Or if you're listening to music on Spotify or YouTube, you rewind and you play it back again. Like that is the data source. And I'm talking about the source for the first step, right? Not the hot potato source for the sources for the multiple steps afterwards, for the intervening steps, not that. But the first step. If the first step is actually the data source which is outside your system, if that source supports rewind and playback, then you have a much better possibility of guaranteeing exactly once processing. And we'll take a look at that when we start talking about the technologies of PubSub and Kafka and etc. But this is a very important consideration. And this consideration allows you to give guarantees of certain types. Okay. The next best practice that you have to pay attention to is the fact that over a period of time, based on your logic that you write here and the logic that you use to maintain the state could get polluted. Meaning, as the application keeps doing its thing without being restarted, without being reset, the state could get partial updates based on the tolerance that we were talking about. Remember, we spoke about can the state tolerate inaccurate data? Over a period of time, as more and more inaccuracies frequent, you feel that finally the state is actually completely disconnected from the guarantee in a way that's significant. At that point, the state is said to be polluted. So, in which case, you will have to take a call on, do I reinitialize the state? Or do I start all over again? Or do I continue? That depends upon the application logic. So, as an example, the customer is shopping on the e-commerce site, and you've actually maintained state about what is the historical behavior of the customer, what does he spend, whether he's loyal, and what is the current shopping cart, right? But for some reason you missed the loyal customer update because that data didn't reach you in time, right? And then like 3 more transactions happen, 5 more transactions happen, at which point you don't keep track of the loyal customer information anymore. You start to treat the customer as though he's a new customer. That could be bad because then the customer is seeing information which treats him like yet another new customer, and he might feel that that's not preferred treatment at all, so I don't like it at all, so I might feel offended, etc. So that's an example of state pollution. Okay. The last best practice here is to worry about what's called as hybrid. So hybrid refers to the fact that some of your source systems, some of your data processing systems could be in different environments. So we spoke about cloud earlier in week 1 or week 2. The typical scenario that you see in a big enterprise, in a big company, is that the data source is likely to be on-prem meaning in the data center. But your streaming application, your stream processing stack could be on the cloud. In which case, the entire application to run requires data to come from your data center, traverse over the internet, go to your public cloud, and in the cloud, it leverages the stack that you've built up there. So this is what hybrid means. Hybrid means there's a bit of, one and the other. One and the other refers to the data center and the cloud. And with this kind of a setup, if you have to reason about streaming latencies end to end, it can be quite challenging. Not just because there's a latency associated with going over the wide area network, over the internet, right, to go to the public cloud, but also because now you have to deal with failures that span multiple different systems. So what if the on-prem system fails? What if the data read from your source system fails? What can the streaming application reason about in the cloud? Right? The failure could be because there is a network timeout, or it could be because the packets over the internet are getting delayed, right? And that could be manifesting as failure. Remember I said performance manifests as a resilience issue. So how do you deal with that? Do you restart? Do you just wait for the packets to come in? Do you conservatively assume that the network is timed out? Or do you assume that the resource has failed? It's very, very hard to reason about these kinds of things. So it's a challenging setup, but it's practical as well. So it's something that you have to deal with as you design your application logic. Great. So that's in terms of the context of streaming. So from next video onwards, we'll start taking a look at specific technologies.